Section 1.5 is dealing with applications of quadratic equations. So we're going to go through just 3 examples, and 2 of them are going to have pictures already given, so you don't have to worry about trying to construct them. So let's just read over number 1. A trough at the end of a gutter spout is meant to direct water away from a house. The homeowner makes the trough from a rectangular piece of aluminum that is 20 inches long and 12 inches wide. So just the original cutout of this rectangular piece is measuring 12 by 20. But what he's going to do is make a fold along the 2 long sides. So where I have the dashed lines here, he's going to fold that up and mark it X inches from the edge. He wants the trough to be able to hold 360 cubic inches of water. So how far from the edge should he make the fold? So we have to figure out what X is. And one clue here is 360 cubic inches. That's volume. So we need to know the formula for volume. And volume is equal to length times width times height. And we have that illustrated here. So if we were looking at this just like straight on, the 2 folded sides would look like this, and then this would be the bottom. And it would go, the 20 inches would go back. So each side here, that would be X. So X is going to be the height. The 12 actually is no longer 12 anymore. We need to figure out what this is. Once we fold this up, what would that be? It was 12, but we're taking off an X from each edge. So that would be 12 minus 2X. So 12 minus 2X, we could call that the width. And then the length would be the 20 inches. So I'm going to write this as a function. I want to say v of x, same as just f of x or y, is going to equal our length, which is 20, times our width, which is the quantity 12 minus 2x, times our height, which is x. Or we could say it's 20x. We can move the factors around, times the quantity 12 minus 2x. Now we want that volume to be 360, so that's what we could substitute in here. And now we just want to solve for x. So we're going to have to distribute. So we'll do 20x times 12 will give us 240x, minus 20x times a negative 2x will give us a negative 40x squared. So let's try to solve this by factoring first. I want to move all my terms. Because my x squared term here is negative, let's move everything to the left side. So I want to add 40x squared, and I want that to go first. Then I want to have the minus 240x, then the plus 360 equals 0. Yes, you could still use the quadratic formula, but you definitely want to use a calculator here. We're going to try not to use a calculator. So what can I factor out? Is there a GCF? We've got some really big numbers, so there should be. We can actually factor out a 40. What's going to be left is x squared minus a 6x plus 9. That 40 is of no use to us. We could actually divide both sides by it. So this time I'm actually going to. In class I left it there. So if we divide both sides by 40, we're just left with x squared minus 6x plus 9 equals 0. That looks pretty simple to solve by factoring. So make 2 sets of parentheses. We should have an x and an x go in there first. We could try 3's here. Sign should be the same, and they're both negative. So this is, again, what we're going to just get one solution. We have a multiplicity of this factor. So we just set it once equal to 0. So x is going to equal 3. So we want to answer this. So we're going to say the sheet should be folded 3 inches from the edges. So a lot of times with these now, it's just knowing what formula to use and then incorporate all the information that's given to us. All right, in this problem here, we want to find the lengths of the sides. There's a little bit more to this sketch, so I'll read over it. This is just coming directly from the textbook. So the passage that goes with this picture here, it says the window or a window is in the shape of a rectangle with an adjacent right triangle above. So this whole thing is a window. The length of one leg of the right triangle is 2 feet less than the length of the hypotenuse. So that means the length of one leg here is 2 feet. The hypotenuse, this is a right triangle. Hypotenuse is x. So x minus 2 is how we express 2 feet less than the hypotenuse. Then the length of the other leg is 1 foot less than the length of the hypotenuse, that's x minus 1. We just want to find the lengths of the sides of a right triangle. So think back to what you remember about right triangles and the lengths of the sides. And is there a formula that comes to mind? Hopefully it's the Pythagorean theorem. And if you remember, it's a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. So that's what we're just going to substitute in here. My two legs, I'll write it this way. The sum of the square of the legs is equal to the square of the hypotenuse. So I'll label this here hypotenuse. This is a leg. This is the other leg. So we're going to write this as one leg is the quantity x minus 1 squared. The other leg will give us x minus 2 squared, and then the hypotenuse would just be x squared. So now we have to expand these binomials. If you want, pause the video, and you can try expanding these. We always need practice with them. But if not, you can just remember to write it out this way. This is what it means to square a binomial. And if you do this, you have less chance of making a little mistake. So over here, we're going to get x squared. Then we'll have a minus x on the outside, minus x on the inside, plus a 1 at the end. Next, we'll have plus x squared minus 2x plus 4 equals x squared. Then we have a lot of like terms to combine over here. I'm going to add the x squares first. We'll get a 2x squared. Right here, I have a negative 2x plus a 1. Over here, we have a negative 4x plus a 4. So I was only combining a few terms there. So now we can combine our x terms. Negative 2x minus 4x is a negative 6x. 1 plus 4 is 5. And then I have the x squared on the other side. Now let's bring this x squared over. So I want to subtract an x squared. So we have x squared minus 6x plus 5 equals 0. Again, we'll solve by factoring. We'll have x and x. What's nice is 5 is prime, so we'll just do a 5 and a 1. Signs are the same, and they're both negative. So we'll set each factor equal to 0. And we'll get x equals 5 and x equals 1. But we always need to check our solutions here, because if we go back to the lengths of the sides, when x is 5, we can have a 5. This would be a 3. And this would be a 4, and that makes sense. But if we tried this when x is 1, let me undo what I just did there. If x is 1, 1 minus 1 is 0. We can't have a side length of 0. That would be no length whatsoever. And 1 minus 2 is a negative 1, so that doesn't make sense for the side. So we can't use the 1, but we can only use when x is 5. So that means the hypotenuse would have to be 5. One leg would have to be 3, and these are all in inches. I'm sorry, feet. And the other leg would be 4. And a lot of times in physics, we can create quadratic equations here. So in our third and final example for this section, a toy rocket is shot straight upward from a launch pad of 1 meter above ground level with an initial velocity of 24 meters per second. We're going to write a model to express the height of the rocket s meters above ground level. And I'm going to get you started with one. So we can use this general equation here where s is equal to negative 1/2 gt squared plus this little v sub 0 is just our initial velocity times t plus this S sub 0, S is just our position, so that's our initial position. So G is representing gravity. So G, we're going to use 9.8. Our initial velocity is 24. And our initial position is 1 meter above the ground. So that's what we're going to substitute in here. So now write a model to express this. This becomes S equals negative 1/2 times 9.8 t squared plus 24t plus 1. And we could simplify this part. So half of 9.8 is going to be a 4.9. So we get a negative 4.9 t squared plus 24t plus 1. So there's our model. There's our answer to part A. There's a second part to this. For part B, find the time or times at which the rocket is at a height of 20 meters. We're going to round to 1 decimal place. So what we want to do is take that equation from part A, and in place of that S, we want to put 20. So 20 is going to equal negative 4.9 t squared plus 24t plus 1. So again, I have a quadratic. I want to bring everything over to the left side to make my leading coefficient positive. So I'm going to add the 4.9 t squared. I'm going to subtract a 24t, and then 20 minus 1 is going to give us a 19. And because we have a decimal, we're not going to try to solve this by factoring. Let's use the quadratic formula. And we can definitely use a calculator. So instead of x, we're finding t. So we're going to say t is going to equal a big fraction here. The opposite of b, so that's going to become 24 plus or minus. So with your calculator, go ahead and square 24. Or rather, even negative 24. It doesn't matter. Either one comes out positive. You should get 576. Minus 4. A is going to be 4.9 times C. So on your calculator, go ahead and multiply 4.9 times 19. And that should give us 93.1. And then at the bottom here in our denominator, we'll have 2 times 4.9, so that'll give us a 9.8. So because we're using our calculators, let's go ahead and just do 576 minus 4 times 93.1. So we get 24 plus or minus the square root. Hopefully you're getting 203.6 over 9.8. So now let's go ahead and separate this. So I'm going to sort of just draw 2 branches here. So we want 24 plus the square root of 203.6 over 9.8, and then we want 24 minus the square root of 203.6 over 9.8. And again, this is t equals. So I said just to round to 1 decimal place. So what you could do on your calculators, depending on what kind you have, I would put this first part into parentheses, get that total, then divide by 9.8. And the same thing here, get that numerator total, then divide by 9.8. And when you make an equal sign with the dot, that's what I use for the approximate. So this first one should give you approximately 3.9. And then this one down here should give approximately 1.0. And those are our answers. So we would say the rocket will be at a height of 20 meters at 3.9 seconds. And actually in order here, at 1 second after launch. And then at 3.9 seconds, because it's going to go up on the way up. After 1 second, it reaches a height of 20 meters. It reaches some peak and starts to come back down. And then again at 3.9 seconds after launch, it also reaches 20 meters. So we may do one, maybe two more examples in class of this on Monday, but at least this was a few examples here to help you with any that you're going to see in ALEX.